My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about Kirchhoff's laws. As a matter of fact, when an electric circuit contains two cells or more connected in parallel, we cannot apply Ohm's law of closed circuit to determine the current flowing in the circuit. So we have to use Kirchhoff's law. In this edition, we'll learn about Kirchhoff's law. So let's get started. Kirchhoff's current law. It states that the sum of the currents arriving at any junction point, the sum of the currents arriving at any junction point at any node in a circuit must equal the sum of the currents leaving that point. The sum of the currents leaving that point. At junction point at node A, so in front of you we've got a circuit, very simple one. We've got a node A, or the current entering the junction point is I, the currents leaving I1 and I2. I should be equal to the sum of I1 plus I2. Or we can say I minus I1 minus I2 equals 0. And also we can say, of course, I is equal to I1 plus I2. Kirchhoff's voltage law. Kirchhoff's voltage law. What about it? It states that the total voltage applied to any closed circuit path, applied to any loop, is always equal to the sum of the voltage drops across the individual parts of the path. So we can say sum of voltages aiding current flow is equal to sum of the voltages opposing current flow. That's to say, the algebraic sum of all voltages encountered in any loop equals 0. This was about, Kirchhoff's voltage law. Kirchhoff's voltage law can be applied to any loop, anywhere, any type of a circuit. In front of you, we've got a circuit. The circuit contains two cells. 10-volt cell of internal resistance R1 of 1 ohm. And we've got another cell, 1 volt. EMF of this cell, 1 volt. And the internal resistance equals 0.5. And we've got parallel combination, consists of two resistors connected in parallel, 6 ohm resistor and 2 ohm resistor. Current passing through the circuit is I, and that passing through the 6 ohm resistor I1. I2 is the current that passes through the 2 ohm resistor. Okay, this circuit can be solved using Ohm's law of closed circuit, but we'll use Kirchhoff's laws. Okay, what about this circuit? We want you to use Kirchhoff's laws to find the value of the current I and current intensity I1 and I2. So we want you to find I, I1 and I2. Okay, once again the circuit is shown in front of you. By applying Kirchhoff's voltage law on loop A, B, C, D, E, A. Applying, Kirchhoff's voltage law on loop A, B, C, D, E, A. Okay. So we can say 10, the voltage of the first cell. So assuming or moving, clockwise, 10 minus 1, times x, the voltage drop due to the internal resistance, is the product of the current. Assume the current flowing through the whole circuit is X, and the current passing through the 6 ohm resistor is Y, and of course that the current that passes through the 2 ohm resistor is X minus Y. So 10, the voltage of the battery, okay, minus current flowing is X times R internal is 1, minus the voltage, the battery of the second cell, because it is opposing to the first, so minus 1, minus 0.5 times X, minus 6Y, voltage drop across the, 6 ohm resistor. All is equal to 0. So we can say this equation can be simplified. 9 minus 1.5x minus 6y is equal to 0. So in this way, we managed to obtain the value of y in terms of x. It is equal to 9 minus 1.5x over 6. This is the first equation. And now applying Kirchhoff voltage law on loop A, B, C, F, G, D, E, A. Let me say it again. Applying, voltage, applying Kirchhoff's voltage law on this particular loop. Loop A, B, C, F, G, D, E, A. Once again, 10 minus, of course, 1x minus 1, okay, minus half x minus 2, between two brackets, x minus y. This can be simplified into 9 minus 3.5x plus 2y is equal to 0. This is the second equation. Substituting for y, so x is equal to 3 amperes, y is equal to 0.75 ampere, and of course x minus y will be 3 minus 0.75, it is 2.25 ampere. Okay, this was about the first problem. Another problem, it is shown in front of you. We've got a cell, 100 volt cell of internal resistance 0, negligible internal resistance, and we've got a resistance, okay, 10 ohm resistor, 6 ohm resistor, 4 ohm resistor, and 60 volt cell. Okay, we want you to use Kirchhoff's laws to calculate the value of the current in each resistor. Okay, so we'll apply Kirchhoff's voltage law on loop A, C, B, A. A, C, B, A. Okay, and we'll travel anti-clockwise. Your attention, please. Okay. So 100 minus 4y. What about y? Assume that the main current is x, and part of it passes through the 4 ohm resistor. Let it be y. So the other portion will be x minus y. So your attention, please. X is the current intensity through, the main circuit. Y is the current through the 4 ohm. X minus y is the current passing through the 12 ohm resistor and 60 volt cell. Okay, so 100 minus 4y minus 16x is equal to 0. So we can say 100 minus 16x equals 4y. So y equals 25 minus 4x. Okay. By applying also Kirchhoff voltage law on loop A, C, E, D, B, A, C, E, D, B, A, okay, by applying Kirchhoff voltage law on loop A, C, E, D, B, A, we'll obtain the following equation. 100 minus 12, between two brackets, x minus y plus 60 minus 16x. Okay. So 100 minus 28x plus 12y is equal to 0. This is the second equation. Okay, substituting for y, x is 6.05 ampere, and y is equal to 0.78 ampere, and x minus y will be 5.2635 ampere. Another problem, use Kirchhoff's laws to calculate the value of the EMF of the cell. So we want to calculate the value of the EMF of the cell, V battery. In front of you, we've got 3 cells. One of them is 12-volt cell, the other is 4-volt cell, and they are known, but we have unknown cell. Okay, a cell of unknown EMF, VB. We want you to calculate it. And we've got an ammeter that reads half ampere, okay, and comply to the direction of the current shown in the circuit, okay. The ammeter, as I said, reads half ampere in the direction shown in the figure, okay. We'll apply Kirchhoff's voltage law, loop A, B, C, D, A. A, B, C, D, A. Okay. And we'll go clockwise direction. Okay. So 12 minus 4x minus VB. Okay. And there's something very important I should mention here. As I said, the current read by the ammeter is half ampere. So let portion of it equal x passes through the 4 ohm resistor. And the portion that passes through the 6 ohm resistor must be, of course, half minus x, or 0.5 minus x. So the current entering at node D, at junction point D, is half ampere. The current leaving at this point, a portion x passes through 4 ohm resistor. The other portion, which is 0.5 minus x, passes through the 6 ohm resistor. We'll apply Kirchhoff's voltage law. So 12 minus 4x minus VB minus 0.5 times 2 is equal to 0. So we can say 11 minus 4x is equal to VB. And this way we've managed to obtain VB, EMF of the cell, in terms of x. This is the first equation. When we apply Kirchhoff voltage law on loop G, A, B, C, D, E, G, let me say it again, G, A, B, C, D, E, G, we'll obtain the following. 4 minus 6 between 2 brackets, 0.5 minus x minus V battery minus 0.5 times 2, all is equal to 0. So V battery is equal to, yes, 6x, this is the second equation. And substituting for the value of VB in terms of x, we'll obtain x is equal to 1.1 ampere. And V battery should be 6x, so 6 times 1.1, it is 6.6 volt. And now we've got some questions. We want you to answer this question, give reason for. The first give reason, the resistance of a conductor increases as its length increases. Give reason. Why? When the length of a conductor is increased, its resistance is increased. Okay, the resistance increases with the increasing the length of the wire, because electrons collide with an increasing number of atoms. Electrons collide with an increasing number of atoms. Also, a lone wire can be regarded as a group of resistances connected in series. And when we connect in series, the total resistance increases. So their resistances are added together. That's to say, each piece of a long wire is regarded as a resistance connected in series to the rest of the wire. Second give reason. The resistance of a conductor increases as its thickness decreases. We've got an inverse relation between resistance and cross-sectional area. The resistance of a conductor increases as its thickness decreases. As the thickness of a wire decreases, there are fewer spaces. There are fewer spaces when the thickness decreases. When we have a thin wire, there are fewer spaces between atoms in the cross-section through which electrons can travel, through which electrons can move. Also, in addition, we can say a thick wire can be regarded as a group of resistances, a group of thin wires connected in parallel, so their equivalent resistance decreases. Another give reason, the resistivity of a material is regarded as a physical property. Yes, it is considered as a physical characteristic property, talking about resistivity. But the resistance cannot be considered so. Why? Okay. Resistivity of a material, unlike its resistance, unlike the resistance of the material, is a constant at any given temperature. Resistivity depends on two factors. It depends on temperature and depends on kind of material. So if the temperature is kept constant, it changes only when we change the kind of material. Once again, resistivity of a material is a constant at any given temperature. Okay, and is independent of the dimensions of the wire. Okay, dimensions means length and cross-sectional area. So it is regarded as a characteristic physical property. Okay, but resistance, as a matter of fact, depends on length and area. So it cannot be regarded so. Another give reason, the electrical conductivity of a pure metal is high. Electrical conductivity of a pure metal is high. As a matter of fact, there are many free electrons that are not bound to any particular atom. Free electrons mean they aren't bound to any particular atom within the material. And now we've got a different type of questions. Prove that the electric energy supplied or converted by a device, consumed by a device, is determined from the expression, from the relation VIT. V is the potential drop, potential difference. I is the current intensity, and T, of course, is the time. We want you to prove that electrical energy is determined from the expression VIT. Okay, it's very easy. It's all easy for you, of course. Potential difference between 2 points is given from the equation equal to W over Q. W is the electric energy. Q is the charge. Potential difference between 2 points is the energy required to transfer unit charge, to transfer 1 coulomb between 2 points. And this way we can say electrical energy denoted by W is equal to, yes, of course, the product of potential difference and a charge, VQ. This is the first equation. Okay, since current intensity is determined from the expression I is equal to Q over T, Q is the quantity of electricity, T is the time, it is the quantity that passes through a conductor in 1 second. Okay, so Q, which is the amount of a charge, is equal to the product of current intensity and time. And this is the second equation. From 1 and 2 we can say, yes, electric energy is equal to VIT. So we managed to prove this. Electric energy consumed, electric energy produced by a device is determined, yes, from the equation VIT, V potential difference, I current intensity, T is the time. Another proof that the electric power dissipated in a resistor can be found using the expressions, can be determined using the expression either of the following expression. Power is equal to IV, power is equal to I squared R, also electric power is equal to V squared over R. Okay, first of all, potential difference is determined by the equation V is equal to W over Q, and of course W is equal to VQ. This is the first equation. And current intensity is determined from the expression I is equal to Q over T. So Q equals IT. This is the second equation. From 1 and 2, we managed to obtain electric energy is equal to VIT, but we are talking about power. What is the relation between energy and power? Power is equal to energy over time. It is the rate of converting electric energy, okay? So power equals electric energy converted, electric energy produced or consumed over the time. So it is VIT over T, and of course the time will be crossed out. So power is given from the expression VI. This is the first part of the proof. And of course we've got Ohm's law. Ohm's law, V is equal to IR. Okay, so I is equal to V over R. Substituting for I in the equation number 3, I is equal to V over R. So the power will be, yes, I squared R, and also it will be V squared over R. Another type of questions, 3 identical lamps are connected across a battery of negligible internal resistance. 3 identical lamps. Each lamp will be denoted by R, and they are identical, okay? So we've got 3 equal resistors, okay, connected to a battery of negligible internal resistance. Once in series, then in parallel. Okay. Prove that the ratio of the powers dissipated in the 2 cases is, the ratio is 1 to 9. Okay. In series connection, okay, it is shown in front of you. The first step to be taken here, you have to calculate the equivalent resistance. R equivalent, of course, it's all easy for you. It is 3R. Okay. Then we'll calculate the current passing through the circuit, the current intensity denoted by I1. Ohm's law of closed circuit, it is V battery over R equivalent. So V battery over 3R. Okay. And how to determine the power? we've got three expressions. One of them is I squared R equivalent. Okay, so I1 is squared R equivalent, and I1 is equal to V battery over 3R. So V battery over 3R all squared times, yes, 3R. Why 3R? We are talking about the whole circuit. So the equivalent resistance of the whole circuit, which is equal to 3R. 3R, okay. So the power will be VB squared over 9R squared times 3R. And this can be simplified into VB squared over, yes, it is over 3R. So we managed to determine the power in the first case, in the series connection. It is VB squared over 3R. Okay, now we repeat this, but when connecting them in parallel. In parallel connection, first of all, we have to calculate R equivalent. It's all easy. It is one of them over the number. So it is R over 3. And power, it's all easy, can be determined in one shot using the expression VB squared over R equivalent. V squared over R. Applying this on the whole circuit, it will be V battery squared over, instead of R equivalent. Okay, and what about R equivalent? R equivalent is equal to R over 3. So it is 3 VP squared over R. So this is the power dissipated in the second case. Now we'll compare the dissipated power in the series connection to that, yes, in the parallel connection. When comparing the two powers, okay, we'll obtain the ratio, which is 1 over 9. And we've got another type of question. It is a comparison between specific resistance. Of course, you know, specific resistance is resistivity, okay, and resistance. We'll try to compare between a specific resistance and resistance. First point of difference is the definition of each. Definition of a specific resistance or resistivity of a material is the resistance of a wire made of that material. The wire is 1 meter in length and 1 meter squared in cross-sectional area at that stated temperature. Okay, this was about the definition of the specific resistance. What about the definition of resistance? It is opposition to the flow of the electric current. Opposition to the flow of electrons. And second point of difference is the measuring unit. Measuring unit of resistivity is ohm meter, but it is just ohm for the resistance. And the third point of difference, yes, what about this point? Yes, it is about the factors that affect each quantity. The factors that affect resistivity are just two factors: kind of material and temperature. But there are 4 factors that affect the resistance of a wire: length of the wire, thickness of the wire or cross-sectional area, kind of material, and temperature. So there is a major difference between the factors affecting each quantity. And finally, being a characteristic property or not, this is very important point of difference. As a matter of fact, resistivity is considered a physical characteristic property. Okay, specific resistance, which is resistivity, is regarded as a characteristic physical property as it doesn't depend on dimensions of the wire. It doesn't depend on length and cross-section area. It doesn't depend on the dimensions of the wire. Resistance cannot be regarded as a characteristic physical property, as it depends on the dimensions of the wire. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.